But okay, not really any logistics. We have a lab today. We'll get through most of this PowerPoint slide on Faraday's law today. I don't know if we'll get through all of it. Whatever we don't get through, we'll go to next Tuesday, and then next Tuesday we'll start inductors, and we'll see how much of AC circuits I'll get to cover. I don't know. We'll see. That's fine. Whatever we don't cover on AC circuits will likely get kicked out in the test, which is kind of awkward, but I think AC circuits are fairly important, considering it's half of electricity. So.
Hello? I would tell you a joke about perforated paper, but it's terrible. Thank you.
Yeah, that's good. All right. So Faraday's law, we started talking about this last time, and the big exciting thing here is this is how we make electricity. That's like this entire PowerPoint is largely sufficient for you to understand how generators work. You don't really need to know much more. Obviously generators are more complicated than I can cover in 1 week, but this covers the physics behind them. So that's cool. Considering, and I say generators, literally every single way we produce electricity except for batteries and solar panels, coal power plants, nuclear power plants, wind turbines, water turbines, even thermal power. Yeah, everything's just spinning something in your car. So it applies to everything. Now, we reminded ourselves about flux. It was a good time. Reminded ourselves that flux was the integral of B dot dA. I will also tell you, I won't actually have you do this integral, so I will keep the complexity a little simple. We're not going to have any, so this will just turn into B times A times cosine theta in every single case. I am not going to give you any cases where the magnetic field, where you have to integrate. You would be able to do it, we just don't have the time to practice those kind of problems. So, yay, I guess. I don't know. It's a bummer. I was excited about one, but we just don't have the time for me to prepare you well for it, so you're spared. All right, then we found that if you change this flux with time, it makes a voltage. Now, it's not like a real voltage. It's not like a voltage you can, if it's just a loop, you can't really quite measure it per se. That's why we call this EMF. We make something that acts like voltage. It's as if, so for example, say we made an EMF of 5 volts. How do we do it? Doesn't matter, but just say we made an EMF of 5 volts. It's as if there's a potential difference of 5 volts in that circuit. The electrons are experiencing the same kind of situation as if there was 5 volts. So it's kind of a weird thing. There's a reason we don't just call it voltage, but it acts like voltage for all intents and purposes. So cool. How do we make it? 3 ways. We can change the magnetic field, we can change the area, and we can change the angle. We changed the magnetic field. We did a problem on that. So we started actually changing the area. Then we did a problem and we learned about loop. We changed the magnetic field and another problem. And then at the very end, we talked about changing the angle, and we said, how do you change the angle? You spin it. And this is actually how things work. This is how they're making electricity. They spin something. Your alternator in your car, that is a generator. How does the alternator work? It's hooked up by a belt up to your engine, and as your engine, makes your tires move forward, that same rotation is used to spin your alternator, and it produces about 14 volts. So your alternator produces jack squat when the car is off because it's not spinning. Your battery, that's why your battery exists, is like a way to store charge when your car's not running. But in the case of your car, when your car starts running, you can disconnect the battery from the car and it'll still stay running. Why? Because the alternator is applying the voltage. You need voltage to be able to make the spark plugs make a spark so that it actually ignites the fuel. But when your car is running, the battery is doing nothing. That's why when your battery is dead, you don't realize it until you try to turn on the car. That's the only time you really need the battery. Also, if you have the battery can help supplement the current if the alternator can't produce enough. So, fun practical fact for you all. How do you test if your alternator is bad? You just go to your car, and when it's running, take a multimeter, measure the voltage across the leads of the battery. And if your alternator is running, it should be around 14 volts. Your car's battery is 12 volts. If you want to charge your car's battery, you need to be above 12. So if your alternator is bad, maybe it's only producing like 11 volts, which isn't enough to charge your battery. So your battery will just eventually die. But that's a really, really easy thing that you all can do with a multimeter. If you don't have a multimeter, you should buy a multimeter. They're like $20 or something. It's kind of like a calculator. You'll have it forever. It's super useful. You can even get them for free sometimes. Harbor Freight sometimes does some deals or whatever. Get a multimeter if you don't have one. All right. Then we talked about rotation, angular velocity, angular frequencies. 2 words for the same thing. They got regular frequency. Angular velocity is exactly what it sounds like. It's the velocity of the angle. It's how quickly your angle is changing. Frequency is the rate at which something occurs, specifically rotations or revolutions per second. So in your car, when you're driving, you have RPMs. That's kind of like frequency. The units aren't quite right. RPMs is revolutions per minute. This is revolutions per second, but it's easy enough to convert that. If you wanted to figure out the angular velocity, you would need to take your frequency and multiply by 2 pi to make it into radians. The reason for this this equation here is something you all can derive super simple. The units for omega are radians per second. If I want to go to revolutions per second, I just need to get rid of the radians and turn it into revolutions. So I need to multiply this by something that is for 1 revolution, how many radians do I have? 2 pi. And ta-da, we derived it. How do you go from angular to regular? You just divide it by 2 pi. So that's useful to know. All right, and this is the last thing I asked you. Is this the last thing? Okay, almost sorry. I asked you all this question. Hey, how do you write cosine theta in terms of frequency and time? We did it. We then used it. We then generated the flux, and we generated the EMF generated by that. And that nicely segues us into, hey, given this is the EMF generated by a rotating object, 2 pi f NDA sine 2 pi ft. You're like, oh my gosh, that's crazy looking. It's what we derived last time, so you can check that out. It's nothing too bad. It's just got a bunch of letters, but they're anyhow. The question is, what happens if my angular velocity increases? And I'm going to clarify some things. These should be max. So does the max voltage increase? Does the max voltage decrease? Does the voltage change more rapidly? Does the voltage change slower? Or nothing changes? This is my question to you all. And I'm allowing you to pick more than one answer. See what y'all think. Using that equation, what happens if omega changes? Now that answer is in terms of F, but you can convert that into omega using the relationship we just showed. So probably want to write that in terms of W, i.e. omega. It's testing if you understand sine functions.
So it would take half the time for it or one time I woke up
Yeah.
Oh, yeah. Yes. So by changing W,
Yeah.
you get what?
There's also the omega and the input. Like the amplitude and the sine of omega t. For them to get
All right, give y'all about 10 more seconds. Yeah. So where does W show up in this equation? So it's there, it's somewhere else as well. So it's in the sign and it's in front of the thing. When you have something times sign, what's that thing in front of it? So, sign does this. I'm done. The number in front of the sign, what does that correspond to in this wiggle waggle? If I multiply by a bigger number, the amplitude. So that's going to make my and what is my amplitude? What is this an amplitude of? Like, what's this a measurement of? The voltage. So if I make my amplitude bigger, then my max will be larger. Inside of it represents the rate of change of the function. Yeah, so if you make the inside, t is going to increment, time's going to go by a stopwatch. But if I multiply by a bigger number, it's going to reach that 2 pi much quicker. All right, so 5, 4, 3, 2, 1. All right. So this question is testing how well you understand sine and cosine functions, and these are functions you all really need to understand. Because sine and cosine functions are used for anything that repeats itself. And so many things repeat themselves. There is something really fancy called a Fourier transform, which is a super, super useful tool that is you're not going to need to do a Fourier transform in this class. But the Fourier transform is critical to all wireless signals we currently use. I say wireless, every signal. Wi-Fi signals, internet, everything. What does a Fourier transform say? It's kind of a wild idea. Every single function that exists, with some caveats, can be written as a sum of sine and cosine functions, which is like a really weird idea. So as weird as this sounds, you can write x squared as a summation of sines and cosines. Every single function that exists, with some caveats. I don't even know what the caveats are. I just keep saying there are caveats because I know there are. Can be written as an infinite sum of sine and cosine. So everything can be written as a combination of periodic functions as sine. It's just a weird, wild idea. Convince you these are important things for you to understand. So this term here, epsilon, I'm just going to replace the 2 pi f with a w so we can see where the w's at. Great. So there's my w. And so what you all need to remember is this. So this is just like the general form of a sine function. The number that you multiply in front is the amplitude. So, sine does this. It wiggles its way around. If I increase the number in front, that's the amplitude. If I make the amplitude go up, it makes my thing get taller. There we go. So look, W's in front, meaning if W goes up, my amplitude goes up, meaning I'm going to produce more voltage. My max voltage, my average voltage will also go up. The next thing is sine there's a W inside of this. So sine oscillate. When does a sine function repeat itself? What are the angles that, if I start at 0, when does it then repeat itself? What angle? 2 pi. This function says time's going to keep ticking. You start a stopwatch, time's going to keep going. The number in front, if I multiply by some number, the quicker I reach 2 pi, the quicker I repeat myself. So if I multiply by a bigger number, I'm going to reach 2 pi much quicker. I.e., as I increase omega, I make these waves get tighter because I hit that 2 pi much quicker. So not only does this make the max voltage increase, it also makes the sine function squish. So by increasing omega, if my original function's here, my new one would be like some exaggerated one. I have a nice little simulation of a generator that I didn't make, but someone else did, that shows this. This is a very important idea because if you want to make a bunch of voltage, you can't just spin it faster to do it because you run into some problems. So for now, I'll just prove it to you all that doing this. So this is doing the math. It's secretly just doing sine. So y'all can see here the voltage is oscillating according to, in this case, a cosine function. But when we take the derivative, no, this one's sine. Nope, this is cosine. It doesn't really matter. It's all shifted. All right, what I do want to show you is if I decrease omega, if I make it spin slower, the wave gets stretched out and it gets flatter, just like we showed. And then if I make it much higher, it makes it much steeper and much closer together. So this just proves that. Now, this proves it by doing the math that we just did. Now, something interesting here is the voltage flip-flops back and forth. We're going to learn about that. But just a quick aside, this is how electricity is made. This is how generators work. This is how power turbines work. Something very important is that all generators in the U.S., every single one that's connected to the power grid, has to output a frequency of 60 hertz. That is the frequency. If you plug a multimeter into a wall socket, you can actually do the frequency measurement. You can measure the frequency and it'll be 60 hertz, plus or minus 1, like 59.5, 60.5. There is some wiggle room. What's kind of wild about this is that every single turbine, every single generator that's connected to the power grid is coupled together. Coupled together means that if one slows down, it will actually start to experience a force that is not good for it. It's actually a problem. Specifically, this happened with the Texas blackout. So there's a couple years ago where during the winter, there was a really large winter storm and a lot of people in Texas turned on their heaters. How do heaters work? At desperation, they literally heat up wires by just running current through it. So it actually takes quite a bit of energy to heat up things. It's called ohmic heating because it uses Ohm's law, V equals I, R equals IV. Anyway. So many houses were connected to the network and drawing power that it was actually decreasing the frequency. It was making these generators have to work harder, and by working harder, their frequencies, it was harder for them to spin. The problem is, because they're all coupled together, these machines are designed to spin at this 60 hertz. If they are not spinning at the 60 hertz, they can start to be damaged because there's a force involved here. We're going to learn a little bit about that later ones, that this is not free energy. It's not just free to spin this thing. It's not like on a... you can spin it and it'll just spin forever and ever and ever. You actually have to put a force to make this thing spin. You're going to get fought when you try to spin this. There's actually a resistive force to doing so. It's not free. And so these generators feel this resistive force, and if the frequency drops too much, it can cause permanent damage to the turbines and generators. And once a turbine is broken, it's broken. So the only way that you can kind of prevent this from happening is cutting off load, i.e. cutting off houses from the network. So this is something they had to do. They had to selectively pick which places are not going to get power, because if they let all these houses keep drawing all this power, it would cause permanent damage. You cause permanent damage, eventually the turbines break, eventually the whole grid shuts down. And when that happens, to restart an entire electrical grid takes months. You have to spin up each generator kind of one at a time, get them to match their frequencies. It's a really long and not simple process. But I mentioned this as a fun fact, that you can make more voltage by spinning something faster. But actually, if you connect to the electrical grid, you got to make sure your frequencies actually match. And that's something, anytime they're spinning up a new turbine, they have to get it to the right frequency. They have it disconnected from the grid. And then all of a sudden, they pull this once they get it to the right frequency, they pull this massive lever and these things shunt together. And it then connects to the network. But you can't connect it until it reaches that frequency. Otherwise, it's kind of like jumping onto a car that's moving and you're not. It's not going to go well for you. If I want to jump into a car that's going 60 miles per hour, I better be going 60 miles per hour. Otherwise, the car's just going to run me over. So, fun facts. Just complete aside, you don't need to know any of that, but it is critical to the electrical infrastructure in the U.S. So, kind of cool. It's critical to everywhere. 60 hertz is the default. No idea why. Someone chose. It is what it is. All right. Now, we've been talking about it's going to flip-flop. the direction is going to flip-flop. Now I'm going to teach you how to find that direction. So my question first, and we'll make this brief. This is going to sound stupid, but it's going to help us understand this. This negative sign I've been ignoring this entire time. There's a reason it exists. If I multiply 5 times negative 1, what does it turn it into? Negative 5. Great. If I multiply negative 5 times negative 1, what does it turn it into? All right, this sounds stupid, but what I want to get you in the idea of is that multiplying by a negative kind of makes it the opposite. That's the idea here. By multiplying by a negative, we're doing the opposite. So if we look at this equation, what this equation now says when we acknowledge the negative is that I'm going to generate an EMF opposite the changing flux. I'm going to generate an EMF to, in another phrase, oppose the changing flux. Whatever is happening to my flux, I don't like it. I'm going to oppose it. I'm going to do the opposite. That's what that negative sign kind of represents. So now we're going to kind of start to apply that idea, and it's going to make more sense as we do that. But that's the critical idea. We make these wires make an EMF, make a voltage, make a current to oppose a changing flux. This is called Lenz's law, named after some guy named Lenz. I don't know too much about him. And it says exactly what I just said, that we're going to make an induced EMF, which in turn, voltage makes current. So this voltage is going to result in a current to oppose the changing flux. And we're going to have to do a few problems to make sense of this. It is a 3-step process. You have to do every step in the process. You cannot skip it. There is no shortcuts. It is a 3-step. There's no shortcuts that I know of. So the rule is magnetic flux wants to stay constant. Why? Because this is how the universe works. This is not like me pulling any switches or pulling any levers to make this happen. This is just what happens. So if the flux goes up, I'm going to make a current to oppose that. If the flux goes down, I'm going to make a current to oppose that. That's the rule. So we're going to look at this picture on the bottom, and I'm going to use this as an example, and then we're going to do a bunch more examples, because that's the only way to really understand this. So in this bottom, I have a loop of wire that starts in a place of no field, like there's no field in it. So what's the flux right now? If it's above that red circle, no magnetic field, what's the flux? 0, right? Now, whenever we talk about flux, a great way to think about flux is it's how many field lines are going through my surface. That is what flux is. How many field lines are going through my surface? You can almost think of it like a flow. Nothing's actually flowing, but that might be helpful to understand it. Now, as my loop goes down, here is the thought process. Am I getting more field lines or less? Y'all tell me. I start with none, and I go down. Those blue dots are field lines. Am I getting more of them or less? More. Great. Which way am I getting more? Am I getting more out of the page or more into the page? Or what does a dot represent? Out or in? Out. So, first step, we identify what's happening. We're getting more B out. This is the 3-step process. I'm going to show you the process written in words in just a second, but I'm getting more B out. I don't want that. That is the Lenz's law. This is how the world works. I didn't make this decision. It's just how things work. I don't want more B out. That's what the loop is saying, if you personify it. So, how do I cancel out? If I'm getting more B out, how can I cancel vectors pointed outwards? I can make vectors pointed inwards. I can make the opposite of them. So I'm going to make B in. How do I cancel out? I'm like, I don't. So look, there was none. Now when it's down here, there's some. It doesn't want that. So it's going to make some magnetic fields pointed in to counteract that change. Now we're going to use right-hand rule 2.5. How do I make that magnetic field? If I have a loop of wire and it's making a magnetic field into the page, which way is the current flowing in that loop to make that happen? How? If I just drew this off to the side, I have a loop of wire with the magnetic field pointing into the page. How is it making that? Which way is the current going? Clockwise or anti-clockwise? Counterclockwise. Right-hand rule 2.5 is a shortcut. Point your thumb in the direction of field, and your fingers will curl in the direction that the current will flow. This only works for loops. Loops can be anything that's a close thing. So, just to kind of show it over here, if I want to make this current flow, If I want to make this field, I just point my thumb in the direction of that field. Which way is current going to go? Clockwise. Boom, that's what's going to happen. As this thing goes down into the field, it will make a current clockwise until the change no longer is happening. It will only do this to counteract the change. If there is no change, then it doesn't care. So this is going to make an I clockwise. Boom. So that's what's going to happen here. Now, once it's in the field, if the field is uniform everywhere, it'll stop making the current. It will only make a current to oppose a change. If there is no change, then nothing happens. There has to be a changing flux to make this happen. So now we're going to look at a variety of situations to practice this. Oh, so sorry. Here's it explicitly. First, draw a picture. If I don't give you a picture, draw one. You need a picture to do it. Just not it. You're going to make your brain work harder and probably make more mistakes if you don't have a picture. Then we're going to do the steps I just mentioned. Am I gaining or losing field lines, and in which direction? And what direction are these field lines? We just did that last time. Am I getting more or am I getting less? Now I'm going to make a field to oppose that change. If I'm getting more, then I need to make fields the other way to cancel it out. If I'm getting less, then I need to make more in the original direction to counteract that change. Then use right-hand rule 2.5 to figure out the direction of current. There is no shortcuts to this. You have to go through every step. You have to determine if I'm getting more or less. You have to determine how to counteract that. You have to use right-hand rule 2. You have to then figure out the direction of current. And you're welcome to not use right-hand rule 2.5, but that just seems like an unpleasant decision. I don't know. You're making your life harder. To remind you all of right-hand rule 2.5, it's the shortcut for any loop of wire, circular loop, square loop, wiggly waggly loop. It doesn't matter. Curl your fingers in the direction that the loop the current's going, and your thumb points in the field. It goes backwards, though. I can put my thumb in the direction of field, and it'll tell me the direction of current. The rule works both ways. So, in this case, we're going backwards. We're going to find the direction of the field I want to make, and our fingers will tell us the direction of the current necessary to make that happen. All right. Now, here's 6 different examples to try this. And I might make one more because there is a certain case missing I'd like to look at. So the projectors in this room the contrast isn't as good. So this one is the first one we're going to start with. What this is a bar that's sliding on some rails. It's an odd situation. Does this happen in the room? No, but whatever, it's fine. Let's just test the idea. I got a bar sliding on some rails. Those rails are open on the right side, but they're closed on the left side. Why does that matter? This is a loop right here. There's my loop. You need a closed loop. This only works with it. You only get a flow of current in a closed loop. We will see a case without a closed loop at the very, very end of this. We don't get a current, though. So great, it's sliding to the left. So this one we're going to kind of do together, and then I'm going to have you all try some of the other ones yourself. So as this slides to the left, did I get more field lines or less field lines? I got less B. In which direction was this magnetic field? Out of the page or into the page? I'm getting less B out. As the loop gets smaller, I get less field lines. Cool. Step 2. Counter that. I'm going to let you all actually do the next 2 steps. You got this. Counteract that change. How do I counteract that? And then try to figure out how to make a current to make that happen. So we don't like that. We don't like that we're getting less field lines. So how do I keep it safe? I'm losing field lines. How do I keep it safe? Yeah. Going in, right? So if I create going in, that's going to cancel out even more. Oh. So you want to, if you're losing them, then you need to make clear. Yep. Okay. Yep. So then to make us Yeah. What do y'all think? Why? So give me step 2. If I'm making less field lines out, how do I counteract that change? Great. I'm gonna make more out. How do I make more out? Then we do counterclockwise to make that happen. All right. What do y'all think? We're getting less V out, so how do we counteract that? So if I put more V in, that's gonna make even less. That's gonna. So let's say we started with 8 lines that were pointed out. Sometime later I have 5. I didn't like that. I went from 8 to 5. How do I keep it? I'm gonna make more out. So if I'm losing field lines out, I don't want to lose. I want to keep it the same. So I'm gonna make field lines out to counteract more field lines out. And then it goes down. How do I fix that? Add more money budget. So I'm going to make more V out. Which way is the current going to flow to make that happen? You have to do right here. This bar is sliding to the left, and it's a closed loop on the left side. It's an open loop on the right side. So, my original loop was this. Then a little bit of time, this bar is sliding this way. So I showed the bar slowly. It's making it look smaller and smaller and smaller. So I'm getting less of these field lines. How do you get it? I don't like that. So I'm going to make more going out of the way.
No, you do not want to take it. You are making. No, take it with Mazumdar. Do not take it.
All right.
Naders, I'm in Nader.
So, analogy, if I'm losing field lines, if I'm losing money in my bank account, what do? I put more money in my bank account. Counteract the change. How do I counteract losing? I make more of it. I make more of it out of the page. So I'm going to make more dots to counteract what I was losing. And this is going to make a current counterclockwise to make that happen. How do I make a magnetic field lines pointed out of the page? Right-hand rule, put your thumb out of the page. Fingers will curl in the direction of the current. The key here, figure out how much am I losing or gaining? Counteract. If I'm losing, make more. If I'm gaining, make them in the opposite direction to cancel them out. Those are the only 2 scenarios. Now try this one, and this one is a little funky, like drawing this I drew the area vector for you all. I have a loop. This loop is not like this. This loop is flat kind of in the page. The area vector points up. So this loop is like a hula hoop that I'm holding horizontally. The area vector points up. The magnetic field points out of the page. I'll give you all a few moments to think about what's going to happen here as I take this loop and I move it to the right.
More in one direction or more in the other direction to counteract the other one.
If it makes any at all.
Okay.
You do if you do the work.
Yeah, the current can only flow along the wire.
Yeah,
So
to lessen the force caused by the change in flux, you have to add another force.
not force. It's just we're gonna learn at the very end of this PowerPoint why this is happening with forces. Like we're gonna think about in terms of forces at the very end of this.
To get it back to before anything moves the field, it's always another field that needs to be created, right?
So to kind of jump to why this is happening, there's charges in this water. These charges are moving in the direction of the magnetic field. What happens to charges that are moving in a magnetic field? They experience force. That force results in a magnetic current. Now we don't have to go through all of that. This is kind of short, right? But that is the fundamental. It's because a force on a moving charge will make it move. What is the definition of moving charge? But this is a shorthand way without us having to like go through. All right, so I'm gonna give you all a disappointing answer here. Maybe it's disappointing, maybe it's not. I'm gonna remind you all. So if this loop is horizontal and the field is going in plane with it, how many field lines are going through my circle? 0. No field lines are going through this loop. Why? I need a cable. I'll use my cable here. This is fine. If I have a loop of wire in my magnetic, so look, if my magnetic field's pointed at me right now, then all of it's going through this loop. Yay. That's not what this problem is. This problem is the loop is sideways. How much of the field lines are going through this loop when it's like this? Nothing. You know, you can think of it like if I wanted to blow a bubble. The wind was blowing. Look, if I try to blow on this, I'm not going to make any bubble. No flux is going to go through this. I have to turn it this way. This problem has the loops like this. And to connect this to the math, if you're like, why is it not you like the math better? Remember that the definition of flux is B times A times cosine theta. In this specific problem, theta is 90, so there is no flux. I start with no flux, I end with no flux. It's happy. And we're using this definition conceptually. Flux is how many field lines are going through it. That's what flux is. More field lines, more flux. Less field lines, less flux. Here, no flux. At the end, no flux. Who cares? All right, try this next one. It should look familiar. I got a loop going down from a place of no field to a place of some field. The only answer I care about is the one at the end. I mean, I care about if you knew the process. But your end goal is, what is the direction of current? That's the question. What is the direction of current? You got to go through the 3 steps to answer that question. Will the current flow clockwise, counterclockwise, or not at all? Those are the only 3 possible answers. Sure. So the question goes as this goes down, am I getting more or less field?
You need to generate more that are going in order to counterbalance.
I want that. How do I counteract it?
Yeah, if you have more
Into the thing. That's a 3-step process. As you do it more and more, it becomes more natural. It's not a complicated process.
So do you know what the magnetic field is?
Three decisions.
we're having more of the flux is going down. So guys, in order to keep these
All right, this one's clockwise. Why is it clockwise? I'm getting more out. I don't like that. How do I counteract more out? I make some in. How do I make some in? Thumb, clockwise current. This is the 3-step process. What's happening? More or less, counteract it, make a current. All right, try the next one. I got a rod moving to the right. It's kind of like that original setup. This rod on rails, we're going to see this a bunch. It's a good, we call them like toy problems. It's not like a real world problem, but it helps us test our understanding. You got a rod moving to the right. It's closed on the left side, so that's our loop. Am I getting more field lines, less field lines? Counteract it, make a current. Write down each step. The more you hold your head, the more you
I have to do No, I think I have yeah. I think if I added a GP, it'd be like the last thing. Those were recommendations that oh, I have to write that down.
All right, so there's the answer. I'm getting more field lines out. I don't like that. So I'm going to make some B in to cancel it out. That makes clockwise current. How do I know that I'm getting more B out? Imagine the rod's over here. Now there's more dots inside it. More dots means more. All right, this next one, the rod is not moving, but the B is increasing. Now, when we say that a magnetic field is increasing, that does mean it's making more dots. When I say more field, it means more dots if it's out of the board. If it's into the board, the number of field lines corresponds to the strength of the field. Just like, you can imagine wind, fast wind, you draw a bunch of arrows for a fast wind and like a few arrows for a slow wind. It's a very, hopefully an intuitive idea. If B goes up, we should draw more of those fields. If the B is going down, we should draw less of those. That's how we would like to draw it out picture-wise. So go ahead and think through that one, and then I'll give you the answer in just a second.
It's like more compact, right?
Yeah. These lines are all like hypothetical. Are they real? I don't know. The more I learn with physics, the more I'm like, oh, it's made up. But it works.
I hate how much variety there is with vector fields showing like how strong they are sometimes.
Oh, without like the length of the
they'll either normalize the lengths and then use a color code or
I mean, it's the best we could.
Yeah, it's hard. Yeah. Not much you can do.
3 brown 1.
Yeah.
Such good visualization.
I love it.
You wrote a whole Python.
Man, yeah.
It's
I love
wild. I don't know if you watched any of his stuff. It's a YouTube channel where we get really in depth on some physics and stuff. Like really.
The animations are like.
He wrote a whole Python package just to make really nice animations, and it's what like the de facto one we use now for visualizing stuff. You can do like everything, draw lines, make it thicker, thinner, make them. Yeah.
It's very easy to use.
You can color things. You can make font like change into other font. Like. All right. So if B is going up, I'm getting more B. More B out. How do I counteract that? Make B in. How do I make B in? I make my current's going to be clockwise. So yeah, when we say this field, the stronger the field, the more arrows there are, or dots in this case. All right, the next one is pretty simple. It's the same as B. My flux is 0. I don't care what's happening. I could increase B all I want. None of it's going through it in the first place. So what happens here? Nothing. Why? Because it starts with 0 flux. I don't care what you do to the field. It's not going through it at all. I want to give you all one more example that I don't have here, and then we'll do some clicker questions on it. The one example I don't have here because it's a pain in the butt to draw, but I'm going to go ahead and draw it. I have a loop that can spin. So I have some magnetic field that's pointed out of the page, and this is where it gets a little bit of a pain. This thing is going to spin about the axis as shown. Which way will current flow? Will it flow clockwise or counterclockwise? As this thing spins, am I getting less of those dots or more of those dots? And what do I need to do to counteract that? Make it happen. It won't matter either way. The nice thing is it doesn't matter which way it rotates, you get the same answer. So as it rotates, so think of eventually, we're just going to do right now. Right now, So as it rotates, I got this field coming out of it. As it rotates, am I going to get more of those dots or less of those dots? I'm going to get less of them. You can imagine the extreme. Eventually, it'll be oriented this way, and it won't get any dots at all.
For now, for like,
Just this instant. Just this instant. Yeah.
but like if it were like spinning constantly, then it would be flip-flopping.
It would exactly. When I'm flat like this, then when I start rotating, I'm starting to get more. And I don't want more, so it's going to actually make it curve the other. And that's how we make AC current. It goes one way, then the as it's spinning, the current flip-flops direction in a sinusoidal way. All right. So as this thing spins, originally it's getting all the dots. But as it spins, I'm going to get less and less and less of the dots. Why? Because it's going to start to become perpendicular to the area vector becomes perpendicular to the field. So I start with, I'm getting less B out. In this case, less B out. How do I counteract that? I'm going to make B out. How do I make B out? I'm going to have a current that flows. I have to be careful here. Counterclockwise. Now, what's really important here is as this thing rotates, eventually it'll reach a point where it has no dots going through it. What's going to then happen as it keeps rotating? As it keeps rotating, then it'll start to get more. It doesn't want more. So it'll make some the other way. So the key takeaway here is if we go back to the thing I showed you all before, the current flip-flops. These little red arrows, I know it's kind of hard to see them, but the current is actually flip-flopping as it goes through it because in this place it alternates between getting more field lines and less field lines. So the current will alternate to counteract that change. And this is why all generators make AC voltage. The only way that we make DC volts, so AC means alternating. It goes back and forth. So when you plug something into like the wall, the current in the wall, the voltage in the wall makes the electrons wiggle back and forth. They don't actually travel in one direction. They just kind of wiggle back and forth. How do you make it into like a one-way street where it's just going? You have to use a variety of things. Gosh, I forget the names of them. They mentioned commutator here. You can use a diode. A diode only lets current flow one way, but you lose your energy on the back half and whatever. I'm not going to get too much into that. All right. Loop of wire flat on the page starts in a place in a magnetic field. It then enters a field pointed into the page. Show a current go. I didn't give a picture to you. Draw one. Make it happen. Flat on the page is what it sounds like. You just draw a circle. Yep, good. Yeah, good. Perfect. What else? What?
It's not always opposite. But if you're using it, you want to gain in that same direction. Right.
It's really hard to get it rolling, but once it does, I think it goes pretty smooth. All this right here. It's really important. There is no way around it, but
You're always trying to counteract your chances.
all right. What do y'all think? right, give you all about 20 more seconds. I'm very happy to see this, how this is going. Teaching this, I was just telling TA, it feels like pushing a big ball. It's really hard to get the ball rolling, but once you all get this, once you do a few of these, it tends to, the process is fairly simple, but it takes a bit to kind of make it land at first. Hopefully it's feeling that way, I don't know. If not, as always, practice a bunch of them. All right, 3, 2, 1. So what I was very happy to see was that people understood the thought process. We are getting more B in, so we're going to make B out, and that's going to give us a counterclockwise current. Again, the crazy thing with all this is that no one's making this happen. This is just what happens. Now, just to give you all a little foreshadowing of why this happens and connect it to something we've learned about, what is every single material made of? What fundamental particles? Atoms. What are the 3 particles that make up an atom? Protons, neutrons, and electrons. We'll focus on the electrons. There is electrons in this wire. If I move the wire, the electrons are also moving because they're stuck to the wire. Why does that matter? If I have moving charges entering a magnetic field, what was the thing we learned 2 weeks ago? What happens to a moving charge in a magnetic field? It experiences a force. That's why there's a current. That's why we call this the electromagnetic force. That's one of the reasons why. So that, to connect it back to 2 weeks ago, why is this happening? It's because there's charges in this. There's moving charges that enter a magnetic field that's perpendicular to the direction of motion. So they experience a force, and the force is such that it makes a current in this way. But this is kind of a shorter way of doing it than finding the direction of the force in those everywhere in the wire and all that jazz. But yeah, that's the reason that we've already learned. Moving charges experience a force. Force makes them accelerate. Moving charges is current. So, yay. All right, now something slightly new. There's just something, just one small piece here. So I have a north pole of a magnet, and I move it towards this copper coil as shown below. If you're looking at the loop from above the magnet, will it make a current clockwise, counterclockwise, or 0? The only thing you all need to know here, I guess there's 2 pieces. You need to know that the magnetic fields point away from the north side of a magnet. And then you need to know a second thing that should hopefully be fairly obvious. The closer I get to a magnet, the stronger the field. Use those 2 pieces of information. There's no fields drawn here. You need to draw them. You need to determine the direction, and you need to determine if I'm getting more or less of them as this magnet approaches. So it's the same process. Am I getting more or less, in which direction counteract each other? This one is just another one. Take a magnet, fling it up and down, and it makes electricity. I'm just so. I think the
He is getting stronger. He is getting stronger with the distance.
Let's go.
Oh, you're doing that. No bad.
All right, give y'all about 20 more seconds. That's fine. I always want to give y'all a chance. I don't really, doesn't bother me.
No, I just had something due that's gone now. So
All right, 5, 4, 3, 2, 1. So to draw this is what the magnetic field lines look like due to a magnet. They kind of do this like looping thing. And then I know this is way overkill what I'm drawing, but just shows you the sense of it. What's important here is the fields are pointed mostly down. So just to make this maybe a little bit nicer, the magnetic field lines are pointed down. Now, as time goes on, I'm going to get more of those. Why? Because the closer you get to a magnet, the stronger the magnetic field. Why? Because they're the reasons they make. I'm not going to get into the. Hopefully, you're cool with that. Hopefully, you're cool with the closer you get to a magnet, the stronger the field. Hopefully, it's not a big jump. To get into the explanation of that would actually I'd have to explain how permanent magnets work, and I don't want to do that. So, anywho, we're going to make a field to counteract that, which results in a current that's going counterclockwise when viewed from above. You do need to be able to do problems with a permanent magnet. Why? Because we use permanent magnets in the real world. Generators are using permanent magnets, and they're either spinning the magnets or they're spinning the coils. I couldn't tell you which, and I couldn't tell you which one's better for why. That's where engineering stuff gets involved. I actually have no clue what's preferential. It might not be preferential either way, but that's where engineering gets involved. All right. I got a north pole of a magnet, and then I got a hoop. This hoop is, when I say it's spinning like this, it's not spinning like a coin. It's spinning like a steering wheel. This hoop is spinning like a steering wheel. My question to you is, what is the direction of the induced current? Is it clockwise, counterclockwise, or zero? It is spinning like a steering wheel. I really wish I had better scientific terms for how things spin. Yeah. That's when I started to do it. I was like, oh, this is so ugly. I was just like, no, it's draw that.
I don't know if you want like.
You are welcome to. That's what I attempted. That's what I attempted to start drawing, and I was like, "Oh my gosh, this is so many things."
The magnets are moving, then the
Yeah, because you got to draw the whole loop, and then I have to have a loop down here, and then I have to draw the whole loop down there. Because yes, that is better. That's why I started with that, and then I was like,
I guess on top of the reasons.
yeah.
Talking about electromagnetic force. What do y'all think? Is the force getting higher?
Oh, nice.
Yeah.
Cool. No. If you look at that, you close your eyes, I spun it. You open your eyes, if I change it, it looks exactly the same. Alright, what do y'all think? Any guesses? What? Now it's not moving, so am I getting more field lines, less field lines, or
This
no?
one is just like, not, no, it's just staying.
Nothing.
We do. There's no like.
All right, give you all about 10 more seconds on this. It's sounding pretty good. There's so many clicker questions because it's just practice. All right, 5, 4, 3, 2, 1. I've accidentally left this a multiple answer, but there's clearly, these are all individual. I hope you didn't pick multiple answers. These are mutually exclusive. You can only do one of these. Anywho, if I spin the wheel, I am not getting more or less. I'm not changing the flux. Why? A rule of thumb. This is a good rule to follow. If I spun this wheel, if you looked at this, you looked away, I spun the wheel, and you look back, it's going to look identical. If you change something and it looks identical, then probably nothing's going to happen. That's a good rule of thumb for many things. So graded 0. I don't get more, I don't get less. Yeah, we're pretty good on that. Again, this is not spinning like a coin. It's spinning like a steering wheel. The mathematical way of saying this is we have it spinning about its central axis. I can't even say central axis. We sometimes call these primary axes. But even that, I don't even know what this one would be called. Whatever, it's fine. All right. Okay. So now we're going to derive something together. What is the flux to this loop? This loop is the loop formed by MNOP. It's the only closed loop in this picture. It has a width of X. It has a height of L. There's a resistor in it. Doesn't matter right now. And there's a magnetic field pointed into the page with strength V. What is the flux through this loop? The magnetic flux. Oh, I gotta ship it to y'all. I'm not too worried about it. We have. So this is to derive the expression for the
Yeah, because well, actually, DA is pointed out. I don't even know. It's one of them, but either way.
Oh yeah, it's either into the page or out of the page. It doesn't matter. That's a great question. Every surface has two area vectors. Honestly, which one do you pick?
Because the cosine's going to be the same.
It'll be 1 or -1, but in the case of flux, you don't really care. Yeah, if you have a three-dimensional shape, we care about the area vector. The area vector will point like away from the surface, but in this case, it's 2D big. It's arbitrary. But he doesn't know what we do. I'm joking.
You know the circular area of the
Yeah, like does it like wrap up the surface? Like this is what we're trying to do. This is how we're doing it. Yeah.
You just approach out.
Well, that's kind of like a
I would say,
but you're talking
I mean,
about
this,
area that's unclear.
every
I think it's good. I think it's a good.
Okay.
I was just thinking, this is the last step. I don't know, maybe I might have to talk to you. This is the second step to it, but it's like, 100 dimensions, but
Okay.
maybe say like now, maybe you should say now I'm going to say dimensions.
Okay.
But I think it's the last step to it.
Sounds good.
That's the only, if I had it.
Yeah.
Oh,
Yeah, bro.
it's just
All right, 5 seconds. I think y'all got this. 5, 4, 3, 2, 1. So the whole point of this is we're deriving something. Oh, well, there you go. Hopefully you got it. Yeah, we all got it. Flux is BA cosine theta. So, do that. Flux is B times A times cosine theta. Magnitude, cosine theta. B is B, A is L times X. Cosine theta, the angle here is 0 because the area vector points into the page or out of the page. Pick your favorite. So we'll just pick the 0 one because it's nicer, and there you go. All right. Which way would the current move if the rod moved to the right? We've already kind of done this a million times. For the sake of time, I'm not going to. We've done this one a bunch of times. I'm just going to tell you it's going to move. I'll give you 30 seconds to think about it, but I'm not going to do a whole problem. I'll let you actually try it real quick. You got 30 seconds. If you can do it, great. If not, don't worry about it. Well, if not, practice. All right, and the answer is counterclockwise. As the rod moves to the right, I'm getting more B into the page. How do I cancel out B into the page? Make B out of the page. How do I make B out of the page? Counterclockwise. All right. So now, look, we just decided that there is flux. That was kind of the big decision here. Flux. There is flux. Now, reminder, we just derived what flux was. In this case, it was B times L times X. We're going to assume a constant rate of change. So, does my B change? No. Does my L change? No. Does my X change? Yes. So, this is a very easy derivation. B times L times dx dt. What is dx dt? You got this. The rate of change of position with respect to time. It's velocity. We did it. We derived the expression for the voltage in this circuit. So when this rod moves to the right, we get an EMF that's just BL times V. And it just comes from the rate of change of flux. Now, something I want to point out here, and I mentioned this before, this is not free energy. This rod is not trivial to move. If you actually had this system and you tried to pull this rod to the right, you would actually feel it pulling against you. Why is it pulling against you? Because of the magnetic force. You got moving charges. You are trying to make charges move in a magnetic field. There will be a force. You can do right-hand rule to figure that out for yourself. This is not free. And so to that end, we're actually have some problems to figure out like the terminal velocity or the force required to get a certain velocity. You'll see it when we see it. Look, there it is. We're going to see it. All right. So I like this problem. I think it's interesting. It gets to the idea that this is not free. There is a force that's going to oppose it. So a conductor of length L and mass M can slide along a pair of metal guides connected by a resistor R. So you can see the picture of it. I got this metal bar, and it can slide up and down. There is a uniform magnetic field pointed out of the page, and the rod is experiencing gravity. It's on Earth. You can ignore friction, though. Direction of the magnetic force on the rod. And then find the equation for the terminal velocity. Now, jumping to part B might sound like a big jump. But for now, just try to do part A. And my hint to you is what is in What do we have inside of a, what kind of charges do we have inside of a rod? Well, okay, sorry, this gets a little funkier. Let's think about it this way. As this thing starts to fall, we're going to get a current that's induced. So you all need to do that step first. So my first question to you all is, as this thing starts to fall, we actually need to go through this process first. As this thing starts to fall, you need to go through the process. It's going to make a current. What's the direction of that current? Clockwise or counterclockwise? That's the first step. It doesn't tell you to do that. I'm telling you, you need to do that. It's necessary to solve this problem. So go through the normal process. Find the direction of the induced current. Will it be clockwise or counterclockwise? Spend some time on that. And then if you figure that out and you want to move on to the next step, if you know the direction of the current on the bottom, if I have current in a magnetic field, what happens? This problem is much easier if you draw it on your paper and you draw the direction the rod's going to move and you draw the direction of the field. The more you try to keep in your head, the less space you have to think. Free up space. Put it on paper. Yeah. Yeah, so we're not quite at A yet. To figure out the A, we got to find the direction. So let's see. So otherwise,
No, out of the page.
Well, it's both.
Yeah.
But I know that you say epsilon equals whatever the ratio is at.
Potential difference.
We don't have like
Because if we can't,
we didn't
right?
charge.
Yeah.
What did you get the fourth? This is the part.
Oh, yeah.
Not that they can fall. Maybe we'll make it have something. Yeah, you just go in with this. The idea is to know does it magnet
What
fall?
did you get? Clockwise?
It makes
Yes.
Okay, and then so you turn wrong, you point to the left.
all right, so hopefully you drew some things. This thing's going to want to fall. Why? Because of gravity. It's going to fall. Which way is the field? Out of the page. Why? Because it says so. The field is the same everywhere out of the page. So as it falls, it's going to get more dots. I don't want more dots. How do I cancel out the dots? I make some X's. The direction of current will be clockwise. I clockwise. Why? Because it's counteracting that change. This is a very, if you don't know the direction of current, you can't solve the rest of the problem. I mean, you can make some intuitive guesses. So if the current is clockwise, let's just draw that on here. My next hint to you all is I have a current going clockwise. I have that gray bar is a current carrying wire in the presence of a magnetic field. 2 weeks ago, we learned that when you have a current carrying wire in a magnetic field, it experiences a force. What is the equation for that force? So that is, you need to find both the direction of it. So part A, what is the direction of that force? I have a current to the left. I have a magnetic field out. Find the direction of force in a current carrying wire. And then part B, what's the equation for that force? That force will be in a certain direction. You have a force of gravity that's in another direction. I have two forces. When those two forces equal each other, my acceleration is 0. It doesn't mean I'm not moving. It just means I've gotten as fast as possible. Set up that equation and see what happens. But yeah, first step, you got to figure out the direction of the magnetic force. You got to know the forces. And you'll see it all works out really nicely. So I'll be going around and helping you all with right-hand rule number 1.
You're on the right track.
Oh yeah.
Get the current and the software. You know the right hand rule 1, right? You want to go along with that. And just to sort of along the ride. So if the current is going clockwise, you stress is
All right. So, fingers in the direction of current. My current is to the left. So, gosh, the problem is I got 3 projectors, so it ends up being a pain. I'll do the one over here. So I'm going to put my fingers in the direction of current. The current is to the right. I need to swing my fingers in the direction of field. My fingers can only swing one way. So fingers in the direction of current. I need to be able to swing it towards the field. Which way is the force? Upwards. So what's really cool about this is as this rod falls, the magnetic field actually exerts a force on it, pushing it upwards. There's a force pushing it upwards, and there's gravity pulling it downwards. Now, I've gotten a great question. Does this mean it'll ever stop? And it's a good question, and let's just think about it. If this thing stopped, what's going to happen to my current? There's no more current. Why do we get a current? Because this is falling and changing the flux. So if you stop moving, you stop making a current. If you stop making a current, there's no more force upwards, which means it would go back to... So it will not stop, but it will reach a terminal velocity. What does that mean? It will reach a maximum velocity and stay there. It will reach a point where it no longer gets faster or slower. It is falling at a steady rate. So when I first drop this, it's going to fall, and it's going to get faster and faster, but it'll reach some steady velocity. Now, the question is, how do we find that velocity? Newton's second law. Sum of forces equals ma. What is my acceleration if I am not speeding up or slowing down? 0. This is a free body diagram problem now. I have a magnetic force up. I have a gravitational force down. They are equal to each other such that they accelerate. That does not mean I'm not moving. That just means I'm not getting faster or slower. That's all that means. Do not get in the habit of If my forces are equal, that nothing happens. No. Just means you're not getting faster or slower. Set up that equation, y'all. FB plus negative FG equals MA, but my acceleration is 0. What is the equation for the magnetic force on a moving rod? Oh, look, it's the last slide. Sorry, that's not it. That's not the force equation. What is the equation for the force? You all know the equation for the force. What's the force on a current-carrying wire in a magnetic field? Yep. So there's a couple steps here. For the sake of time, because we are nearing the point where I want to start the lab, I'm just going to finish up this problem real quick. But I really like this problem. This is a problem that has a bunch of steps to it, but every step is one that you all are able to do. This is kind of as complicated as it gets, in my opinion. But yeah, we don't have too much time, and I want you all to do the lab. So, all right, someone remind me, what's the equation for the force in a current-carrying wire? It will be QVB. That one's for a moving charge. That is correct. What if it's a current-carrying wire, though? IL. There's the equation for the force in a current-carrying wire. Now, the question is, I have B. I have L. What is the value of the current? So now we have to find the current. How do I find the current? This is the first question I asked you all like way up in the PowerPoint slides. Given an EMF, given a resistance, how do I find the current? V equals IR. So I is going to equal the EMF over R. How do I find the EMF? Now we can look at the last slide. What is the EMF? What is the electromagnetic force generated by a moving rod in this situation? It's BLV. You just put the stuff in and follow the train of logic back. All right, so we'll kind of leave it there. I'm not going to solve, like the rest of this is just plugging it in. The train of logic is set up for you all. You do need to remember the force of gravity is M times G. That's the only equation not on this PowerPoint that you need. But we'll go ahead and take a few 5-minute breather. We'll leave the rest of this for Tuesday. We already did more than we needed to. And then we'll do a cool lab. You all can go ahead and join the groups if you haven't done so already. 3 people to a group, all that jazz. But we'll start up the lab in like 5-6 minutes.